Good evening and Happy New Year's. As we step into the new year, researchers across multiple fields are taking a fresh look at the world around us, not by chasing dramatic breakthroughs, but by refining measurements, improving dating methods, and re examining evidence we thought we already understood. These adjustments matter. Timelines of human history are shifting, sometimes by thousands of years. Early societies are showing levels of organization and complexity we once overlooked. Patterns that were dismissed as random or insignificant are starting to make sense under closer scrutiny. In science, precision can rewrite what we thought we knew. In archaeology, careful reanalysis is revealing civilizations far more advanced than previously believed. Even the most familiar objects and documents are telling new stories once we apply modern tools. Tonight, we'll explore discoveries that challenge our assumptions, uncover the hidden structures of nature and human achievement, and take a journey from the measured and methodical to the strange and mysterious, showing us how much more there is to see, understand, and imagine in the world around us. This is where the story of this year really begins. Not with a single discovery, not with a breakthrough headline, but with something quieter: measurement. Because across science this year, researchers didn't so much discover new phenomena as they learned how to look more carefully at what was already there. In physics, astronomy, archaeology, and climate science, new instruments and refined techniques are forcing scientists to revisit assumptions that were once considered settled, not overturned, recalibrated. And that distinction matters. Take timekeeping. Over the last few years, physicists have pushed atomic clocks to levels of precision that were once considered beyond theoretical limits. Optical lattice clocks, which measure the vibrations of atoms using laser light, are now accurate enough to detect changes in time caused by differences in gravity over distances of just centimeters. That means time itself moves measurably faster or slower depending on where you stand. This isn't abstract. These clocks are now sensitive enough to register Earth's changing gravitational field as ice sheets melt, groundwater shifts, and even as tectonic stress subtly redistributes mass beneath the surface. In practical terms, that precision feeds directly into GPS systems, satellite navigation, and Earth observation models. In scientific terms, it allows researchers to test Einstein's predictions about gravity and time at scales never before possible. The physics didn't change, the clock did. A similar story is unfolding in Earth science. Satellite missions designed to measure gravity, ocean height, and surface deformation are now resolving changes that used to blur together. Instead of seeing broad trends, scientists can separate overlapping signals, distinguishing seasonal variation from long-term structural change. For example, researchers can now track how water moves through river basins, aquifers, and ice sheets with enough clarity to refine climate models and improve flood and drought forecasts. Again, the planet didn't suddenly behave differently. Our instruments stopped averaging away the details. In biology, advances in imaging have rewritten what scientists can observe directly. Techniques like cryogenic electron microscopy allow researchers to freeze biological molecules in motion and visualize their structure at near atomic resolution. Processes that were once inferred indirectly, such as how proteins fold, bind, or malfunction, can now be watched in detail. This has already led to more accurate models of disease mechanisms and faster pathways for drug development, not because biology changed, but because guesswork was replaced with observation. The same refinement is happening in material science. Using in situ electron microscopes, researchers can now watch materials change at the atomic level as they're heated, stressed, or exposed to radiation. Cracks, phase shifts, and failures no longer have to be reconstructed after the fact. They can be seen as they happen. That matters for everything from aerospace engineering to battery technology, where tiny structural changes determine performance and safety. And this precision has reached archaeology as well. Improved radiocarbon calibration curves, combined with Bayesian statistical modeling, allow archaeologists to date sites with tighter confidence windows than ever before. Layers, once grouped into broad centuries, can now be resolved into narrower timelines. In some cases, settlements, thought to be separated by generations, are now understood to have overlapped. In others, technologies believed to emerge sequentially appear to have coexisted. History didn't rearrange itself. The timeline sharpened, This is the pattern running through science right now. Not dramatic revelations, not overturned laws of nature, but quieter corrections, better clocks, clearer lenses, more accurate margins of error. And when measurement improves, we get less certain about what we know, but understanding gets deeper. Which brings us to the next question researchers are now confronting. If our measurements of time, material change, and environmental signals were just slightly off, what does that mean for the earliest chapters of human history we thought we already had figured out? Because once precision improves, even the distant past starts to shift. And that's exactly what scientists are now seeing. For decades, much of early human history rested on broad timelines. Not because archaeologists were careless, but because the tools available at the time forced them to work with wide margins of uncertainty. Centuries blurred together. Sites were grouped by rough errors. Cause and effect often had to be inferred rather than demonstrated. That is, slowly changing. One of the biggest shifts has come from improved radiocarbon dating itself. Radiocarbon dates were never static. They rely on calibration curves, which correct for changes in atmospheric carbon over time. As scientists gather more data from tree rings, ice cores, and marine sediments, those curves get sharper. In recent years, updated calibration datasets have tightened date ranges across large portions of prehistory. That has forced archaeologists to revisit conclusions that once seemed settled. In parts of Europe, for example, revised dates now suggest that early modern humans and Neanderthals overlapped longer than previously thought. Cultural transitions, once assumed to be rapid replacements, are now understood as prolonged periods of coexistence and interaction. The artifacts didn't move. Our understanding of the calendar did. Ancient DNA has added another layer of correction. Advances in genetic extraction and contamination control allow researchers to recover usable DNA from remains tens of thousands of years old, even in challenging environments. That genetic evidence has confirmed some long-standing theories, but it has also complicated others. Human migration patterns, once drawn as clean arrows across maps, now look more like braided streams. Populations split, rejoined, and mixed repeatedly. Genetic continuity appears in places where archaeology once suggested sharp breaks, and unexpected ancestry shows up where isolation had been assumed. This doesn't rewrite history. It adds complexity where lines used to be too simple. Improved dating has also changed how archaeologists understand early technology and settlement. Stone tools, agricultural practices, and architectural techniques were often assigned to neat developmental stages. New timelines show overlap instead of sequence. In some regions, for example, hunting-gathering and early farming societies coexisted for centuries, sometimes exchanging tools and techniques rather than replacing one another. That challenges the idea of progress as a straight line and replaces it with something more human: adaptation, experimentation, and coexistence. Beyond dating, new surveying tools have changed what archaeologists can see. LiDAR mapping, which uses laser pulses to penetrate forest canopy, has revealed extensive human-built landscapes previously hidden by vegetation. Entire networks of roads, terraces, and urban planning have emerged in regions once thought sparsely populated. Importantly, these discoveries didn't suddenly make ancient societies more advanced than they were. They revealed scale. Communities that were already known to exist are now understood to have been larger, more organized, and more interconnected than earlier surface surveys suggested. What's striking is how consistent this pattern has become. The past isn't being sensationalized, it's being clarified. As measurement improves, assumptions shrink. As timelines tighten, complexity increases. And instead of collapsing under scrutiny, early human history is proving more resilient, more adaptive, and more nuanced than the simplified versions we inherited. Which raises a broader question. If better measurement is reshaping our understanding of time on Earth, what happens when those same improvements are applied to the universe itself? Because that recalibration isn't just happening in archaeology, it's happening far above us as well. And it starts with how we measure the cosmos. When scientists talk about measuring the universe, they're really talking about two things at once. They are talking about distance, and they are talking about time. Because the farther away an object is, the older the light we're seeing. In the last 2 years, the James Webb Space Telescope has given astronomers the most precise measurements of both of these things that humanity has ever had. Not by looking farther in a dramatic sense, but by looking more clearly and in different ways. Webb doesn't replace earlier telescopes like Hubble. It complements them. Where Hubble specialized in visible and ultraviolet light, Webb operates primarily in the infrared. That allows us to see through dust clouds and detect light that has been stretched or redshifted by the expansion of the universe. This matters because the earliest galaxies don't shine the way nearby ones do. Their light has been traveling for over 13 billion years, stretched along the way into wavelengths that are outside the visible spectrum. This makes older instruments struggle to resolve it. Webb was designed to measure those wavelengths precisely, and it is doing exactly that. One of the most significant results has been the identification of surprisingly mature galaxies very early in cosmic history. Not impossible galaxies, not violations of physics, but galaxies that appear larger, more structured, and more chemically evolved than earlier models predicted at those times. This doesn't mean the Big Bang is wrong. It doesn't mean cosmology is broken. It means the models describing how quickly matter organized itself after the universe cooled may need refinement. Once again, the tape measure changed, not the object. Webb has also provided detailed measurements of star formation rates and chemical composition in early galaxies. By analyzing spectra, astronomers can now detect elements like oxygen, carbon, and nitrogen in galaxies formed just a few 100 million years after the universe became transparent to light. That tells us stars were forming, evolving, and enriching their environments faster than expected, not magically, but efficiently. This pushes scientists to revisit assumptions about how quickly early stars lived and died, and how rapidly galaxies recycled material into new generations of stars. Webb has also entered a long-running debate in cosmology known as the Hubble tension. Different methods of measuring the universe's expansion rate produce slightly different results. That discrepancy has persisted even as instruments improved. Webb's measurements of Cepheid variable stars, one of the standard cosmic distance markers, have confirmed earlier data rather than resolving the disagreement. That's important. It tells scientists the tension isn't a measurement error. It's likely pointing to something incomplete in our understanding of cosmic expansion. What that something is remains open. It is one of many things we simply do not know. This isn't a crisis. It is normal. It's familiar for science. Theories are holding, equations still work, but the error bars are shrinking, and where they overlap imperfectly, new questions appear. That's how progress usually looks. Not as collapse, not as a crisis, but simply as new measurements that tell us something doesn't fit. Just like archaeology, astronomy is discovering that clarity brings complexity. The universe isn't behaving strangely. It's behaving more precisely than our earlier tools could detect. And when precision increases, certainty sometimes decreases before it improves. Which brings us to the edge of what measurement can currently explain. Because even with instruments as sensitive as Webb, there are signals, patterns, and observations that don't yet fit cleanly into existing models. Not violations, not answers, but gaps. And those gaps are where the next story lives. What scientists know, what they don't, and how they're carefully separating mystery from speculation as they move forward. That's next. As measurements improve, something else happens alongside clarity. The unknown becomes better defined, not larger, not scarier, sharper. In science, there's an important difference between something being unexplained and something being inexplicable. And much of what's drawing attention right now falls into the first category: well documented, repeatedly observed, not yet fully understood, fast radio bursts, or FRBs. These are extremely brief, extremely powerful bursts of radio energy originating far outside our galaxy. They last milliseconds, but in that time can emit as much energy as the sun produces in days. For several years, they were a complete mystery. Today, many have been traced to specific galaxies and in several cases to magnetars. These are ultra-dense neutron stars with magnetic fields trillions of times stronger than Earth's. But that doesn't explain every FRB. It explains a large portion of them, but not all. What remains unexplained isn't their existence, it's their diversity. Some repeat, some don't. Some behave in ways current models only partially capture, and others are simply a complete mystery. This is not a failure of science, it's a map with blank regions clearly marked. Then there's dark matter, not a new mystery, but one sharpened by better measurement. We know dark matter exists because of how galaxies rotate, how clusters bend light, and how structure formed in the early universe. What we don't know is what it's made of. Despite increasingly sensitive detectors, dark matter has not yet been observed interacting directly with ordinary matter in laboratory conditions. That absence of detection doesn't eliminate the theory, it constrains it. Each null result rules out classes of particles and narrows the search. The unknown shrinks even as certainty grows. There are also subtle anomalies in large-scale cosmic measurements. Slight asymmetries, unexpected alignments, statistical oddities that sit just at the edge of significance. Most of these eventually resolve into better understood effects, instrument bias, cosmic variance, or incomplete sampling. But a few persist, and scientists are explicit about what that means. Not evidence of new physics, not proof of hidden forces, just things that deserve careful follow-up and further study rather than headlines. What's notable is how restrained the science has become. Extraordinary claims require extraordinary evidence. And most researchers are far more interested in ruling things out than rushing to explain them. Speculation happens, but conclusions wait. That's not hesitation, that's discipline. Across archaeology, cosmology, and physics, the pattern is the same. Better measurement hasn't revealed chaos. It's revealed structure we're still learning how to describe. The unknown is expanding, and it's coming into focus, which leaves one final question. If refinement rather than revelation define this year in science, what does that say about where discovery is actually headed? Because the future may not belong to sudden breakthroughs. It may belong to patience. And that's where we close tonight. If there's a lesson running through science this year, it isn't about answers arriving all at once. It's about how knowledge actually grows, not in leaps, but in refinements. Across fields, researchers didn't overturn foundations. They tightened them. They improved instruments, rechecked assumptions, and accepted smaller margins of error, even when that made conclusions less comfortable. In archaeology, clearer dating didn't simplify the past. It made it more complex. In cosmology, sharper measurements didn't settle debates. They clarified where disagreement genuinely exists. And in the unknowns, from cosmic signals to unseen matter, better data hasn't closed questions. It's narrowed them. That's progress. Not the kind that fits easily into headlines, but the kind that holds. Science rarely advances by dramatic reversals. More often, it advances by admitting where certainty ends and being precise about why. And that precision matters. Because the difference between speculation and understanding isn't imagination, it's measurement. Better tools don't just show us more. They show us what we were wrong about, what we were right about, and what we still don't know. That's not a failure of human knowledge. It's its strength. As the calendar turns, the picture that emerges isn't one of collapse or confusion. It's one of steady correction. A reminder that the universe, the past, and even our own planet don't need to surprise us to be worth studying. Sometimes, the most important discoveries are simply learning how to look again, and that's the science worth carrying forward. This has been For What Is Worth. For more news and information, please like and subscribe.